Hey guys, going to go through a little bit more of the calculus curriculum today, just some of the basic understanding of functions. So I've got a pretty gnarly looking function right here, and what I've gone through so far is where a function is defined and undefined, and I've done limits. So this function is actually pretty much defined everywhere except for at 1 because there's an asymptote there. So this function can never be 1, it asymptotes up. So you'll notice at this point here, the limit as we get closer and closer to -1 is we get closer to 1. Now it's actually 3 at that point, but its limit is 1. Pretty similar here. This one doesn't have the limit, doesn't exist, because as you come to this point from this side, you're getting closer to 3, but as you get closer to 3 from this side, you're getting closer to 0. So the limit is different from the left and right, so it's undefined. The limit is undefined. There is no limit. It does not exist. But the point, this function is actually defined at 3. It's actually defined as 0. So I could have picked either of those points to have it defined as, but let's just say if this function was defined here, it's defined, but it doesn't have a limit. This one is pretty similar to this first one. It's got a limit. As we get closer to 7, we get closer to 1 on the y-axis. So as we get closer to 7 in the domain, we get closer to 1 in the range. Because remember, a function is just mapping this domain to this range. It's just a mapping. Each of these numbers gets some corresponding number in the range. And it's defined as 2 at that point. So just a quick recap of definitions and where this function is defined and undefined. So what I wanted to go through though is discontinuities. So simply put, it's basically a function is continuous if you can draw it without taking your pen off the paper. So this function is discontinuous. I might have spelled that wrong. Discontinuous at -1, at 1, at 3, and at 7. So that's how you'd write it. Discontinuous when x is -1, because you'd have to take your pen off the paper to put that point in and then continue on. It's discontinuous at 1 because it's got an asymptote. You have to go all the way up to infinity, take your pen off and start coming down. So that's discontinuous there. Even though they get infinitely close together. It's discontinuous at 3, right? That's pretty obvious. You'd have to jump up quite a bit to start that next line, and discontinuous at 7. We've got a gap in our function. So if we were to maybe write down a definition, simply a function is continuous if in the interval, going for quite a formal definition here, a, b, it can be drawn without taking your pen off the paper. So a function doesn't have to be defined continuously on the entire real number line. All right, this is the real number line, but it could just be continuous on an interval. So it's actually continuous on 4 to 6, isn't it? So if we were looking at just from here to here in that range, it is continuous over the range 4 to 6, over that interval A, B. So from 4 to 6 is continuous. It's not continuous, however, from 2 to 4. So in general, this function is not continuous. So that's basically one of our definitions for today's lesson. The next definition is gradient. So the gradient of any point on the curve can be estimated by drawing a tangent to the curve at this point. So basically, the gradient here at this point is negative, and then you could just like roll this ruler around and it would be telling you the gradient at all of these points. So here it's 0, gradient is 0, and now it's positive, and now the gradient is very positive, and now it's getting less and less positive, goes to 0. So notice I'm always tangent to this curve, and now it's negative again. So you could have a tangent line there. You could measure that gradient and it would tell you the gradient at that point. You could run a tangent line through here and it would tell you the gradient at that point, and you could do it for all the infinite number of points there along that curve. So let's define this. The gradient of any point on a curve can be estimated by drawing a tangent to the curve at that point. And I've hinted at it a couple times, but the more formal definition of gradient is going to be from first principles, and that's going to be probably tomorrow's lesson. So tomorrow, or maybe the day after. The other definition I wanted to go through with you is maximums and minimums. So most of you would have seen this before, but basically you take a curve and it can either have what is a maximum and what is a minimum. And what's particularly interesting about maximums and minimums is the gradient is always 0. So a maximum or minimum always has a gradient of 0. They're always flat spots, or what we call, I'll put in brackets, stationary points. Okay, so if it was a roller coaster, you would go to have a infinitely small period of time where you'd almost be stationary, and then you'd come back down. Stationary and with respect to your height. Okay, so you'd be momentarily at the peak before you start coming down. So yeah, so you've got a peak or a trough. I think that one's quite standard issue. I reckon. I think that's quite easy to understand. The last one, second last point of today's lesson is concavity. So basically, we can look at this interval. So if we go through here, basically this is concave down, and this is concave up. And remember, that's a minimum and a maximum. So when there's a maximum, we say that this is concave down. So when it's a sad face, we say concave down, and when it's a happy face, we say that it's concave up. And I don't really think that there's anything really we need to go through in terms of concavity. We'll be exploring what happens in concavity a bit more. But basically, there's a special point. So obviously there has to be a place where we change from being concave down to being concave up. And that would be a point like here. And we call that an inflection point, because it wouldn't reflect over that point, but it would inflect. So it's like a reflection. It's like the reverse of an inflection, kind of. So it would not only be reflect, but it would also mirror and be folded down. So we'd call that point an inflection point. So, and that is concavity equals 0. So if this is negative and this is positive concavity, then to go from negative to positive, there has to be a 0 in between, doesn't there? So we call that inflection point having 0 concavity. Okay. The last point I want to make is differentiability. So basically, can you put, remember what I said, you can put a tangent onto a curve and get its gradient. Luckily for us, this has the same tangent all the way down, so we get its gradient. And we can put a tangent anywhere on this curve except for at this point and this point. So differentiability cannot be differentiated at any point where there is a discontinuity, or you cannot get the gradient at that point because the gradient on this side's positive and the gradient on this side's negative, so it's undefined, isn't it? It's almost like our limit theory. So our gradient on this side is positive and it's negative on this side, so it's undefined there. Or where there is a sudden, I'm using some of these words quite loosely, right? Sudden change of gradient. So yeah, that's not a very formal definition of differentiability, right? But it is just some high school understanding for our introduction to calculus. So differentiability is basically you can't find the gradient at that point because it's not defined or it's discontinuous. So how can you get the gradient of that point? And how can you get the gradient of a sharp edge, right? That would be like trying to put the tangent onto a point. Can you put a tangent on a point? No, you can't, and it's pretty similar for that point there. So that is all the definitions we're going to go through now. I'm going to assign a couple of pages for my students to go through to practice those concepts.